why not? All right. Thanks everyone for showing up on time. If other people show up, like Lucas, who just joined, and a few more people filtering in, we'll just start going ahead anyway. So we'll probably see a few more people pop in as time goes. So this month is Keeping Calm When Distributed Consistency is Easy. Talking about a result from the, I believe, early 2010s on doing monotonic consistency. Would anyone like to give an overview of the paper to get us kicked off here?
Sure, yeah, I'll take it.
Okay, great.
So the overarching purpose of the paper is to point at calm, which is a theorem that says that all monotonic programs are programs that don't require coordination, and the inverse is also true, that all programs that don't require coordination to do their thing are also always going to be monotonic. And so they sketch out an overview of the proof, which involves defining a execution environment where they're doing a transducer, where every machine goes through a loop of receiving updates, applying them using their internal relational database, and then forwarding out to the machines that the other machines that they're aware of relevant updates. And then they take that execution environment and a definition of consistency, which is they use the word, what was the word? Confluence, which basically means that the order of operations doesn't matter as long as the outcome of the program is the same. And using those together, they can define what a monotonic program is, and then use that to what is it? Oh, they use the fact that we're using a relational database or relational operations to define what monotonicity means specifically in this execution environment, and then using that they can show that by the argument ahead of time, straightforwardly, it's things are monotonic, and then to show the opposite direction, they show that you need to coordinate things. I'm sorry, I'm botching the sketch of the proof, but
totally fine. You're going off the cuff. It's totally fine.
After they go through the sketch of the proof, they then look at ways to apply calm to a number of common pieces of distributed systems engineering stuff. So they talk about how it applies to CAP, specifically that the set of monotonic programs is one where you can have availability across partition tolerance, because you don't need to worry about making sure that you've coordinated with everyone with the state. You can just do stuff. They talk about how they apply to CRDTs and other distributed design patterns. I was particularly interested in the one thing that was neat was they pointed out how immutable variables in functional programming are an example of monotonicity. They talk about the Bloom programming language, which is sort of focused, a programming language that focuses on providing these monotonic distributed primitives and making it obvious when you're doing non-monotonic things. And finally, they point out that sometimes you still need coordination, and there are even looking through the monotonic lens can be helpful when you're working with coordination, because you can see all of the tricky points. and then they point out some questions that they have about like what can we do for better program synthesis or monotonic focused expressiveness, and analyzing code and looking at potential like probabilistic stochastic applications of Calm.
Amazing. Awesome. Does anyone want to give a definition of monotonicity in this context? It all kind of hinges on this, right?
Well, basically the idea is that as you add input, you are just growing the output. So if you have any set of input and you take a subset of the input, well, then the output of the full set will be the output of the subset will be a subset of the output of the full set. So no matter in which order, no matter which subset you choose, and that's really important. So that means that's what makes it order independent. You could have come with this subset first or that subset first, and you'll have, when you get the full set, you'll have the same output.
And implied in that is that you never have to go back and replay anything, right? Like you don't have to, you can always just keep going forward. There's never a point where you have to say, minute, we need to like go back in history to like, make sure that everything is in order. Everything is already in order because of monotonicity, right?
Yeah,
So
I think oh, go on.
Yeah, so I don't think it's the monotonicity that gets you the commutativity, right? These are separate properties. Monotonicity is saying that we are always moving in one direction and we're never removing stuff.
Yeah, there's not actually any notion of order here. And the definition of monotonicity that they're using is over sets. So it's basically that if you have something that is a subset of something else, then some function applied to that subset is going to be a subset of that function applied to the larger set.
Yeah, so I guess you don't need to know all of the things to answer the question, to put it in a weird abstract way, I guess. And I guess they demonstrate that with the garbage collector example, right? Where in that case, as you normally would think about it, you'd have to know all of the objects to know, are they pointing to like a bit of data or something? But if you can frame it more monotonistically, if that is a word, you'd be, yeah, exactly. You'd be saying you don't need to know all of the elements of the set to understand or to answer the question, I guess.
Yeah, the garbage collection one is a really good example. And there, I think, at least for me, the useful way to think about it is not about you needing to know everything, but about there being a point where the direction that you're moving in can flip around. And in the case of the garbage collection, it's that you can't know that you've found the eventual answer until you've seen everything, because only after you've seen everything will you know that you don't start moving backwards. Whereas in the other example they give, I forget what that is. I think it's distributed locking possibly, or race condition detection.
It's deadlocks, detection, deadlock detection.
Right. In that case, adding more information to the system is never going to essentially negate anything that you've already seen.
It definitely felt like the CRDT state stuff from last time, right? Like the semi-lattice that we talked about. I don't know if, are they
There's
exactly equivalent, is it? Or, yeah, right.
I literally have in my notes, is this a semi-lattice butterfly?
Is this a joint semi-lattice? Yeah.
This is actually something that Brooke and I have chatted about outside of this reading group, because a lot of this work on Calm theorem and monotonicity kind of developed in parallel with CRDTs. And it seems like they tread a lot of similar territory, despite not necessarily collaborating with each other. So there's a lot of overlap with different terminology, but definite connections.
Yeah, the blue mark, they said it's like an OO lens, which I found really interesting. I was like, how is that even, like, what? It doesn't compute to me. How is it object oriented? But yeah, it was quite interesting.
Yeah, so the object orientedness that they're talking about is CRDTs give you essentially encapsulation of the internal state, which is a very object-oriented way of seeing things, and then exposing an interface that says I'm going to add things or do certain operations on it. So they don't mean literally object-oriented, like we're doing Java programming and those classes and all these things, but the essence of OO is about encapsulation and message passing, and so that's in the sense that they mean it. I can't quite find the exact. Oh yeah, here it is. CRDTs are an OO lens on the long tradition.
Yeah, and also I presume the transducers are not like closure transducers or something, or possibly unrelated.
So I think it's a similar idea, right? Where transducer, so even transducers in Clojure are about taking new events and updating some state. And so they're saying it's the same for each node in the cluster. So similar to, say, Elm or Clojure transducers or any of these systems. Yeah. Or I think they actually also mention actors as well. If people have a Erlang Elixir background.
For me, my favorite quote actually appeared at the bottom left of page 5 in section 3.1. And there's kind of two pieces there. First, the second half of Brewer's quote from the CAP theorem. Actually, I'll wait till you have it open. Yeah, so in that quoted block there, you have it highlighted in orange, but the modern CAP goal should be to maximize combinations of consistency and availability that make sense for a specific application. But then the authors of this paper follow up with COM is a positive result in this arena. It circumscribes the class of programs for which all three of the CAP properties can indeed be achieved simultaneously. And I think that that is a very powerful way of putting what I think to most people is viewed as a limitation of distributed systems and applied universally, rather than something that only applies when you consider like the general class of all distributed systems.
Yeah, so do we want to actually dig in and talk through how it satisfies all three? Because that's often, like as they're discussing here, right, is often said that, well, you can only have 2 of 3, and it's taken as a negative result.
Mm-hmm. Yeah, does anyone not know what the CAP theorem is, and do they want a brief description of that first?
Let's give a description anyway.
Sure.
Can you include some history too about who Brewer is?
Off the top of my head, probably not too much.
Okay, or just context of like when it.
Mm-hmm. So CAP theorem was originally an informal result. I forget whether it was actually proven and under what conditions it was proven, but it was essentially like a trilemma for distributed systems, and basically said that the way people usually quote it is that you can choose 2 of 3 for availability, consistency, and partition tolerance. And then because with a distributed system, usually what you with a distributed system, because network partitions are inevitable and cannot be avoided, you are always going to have network partitions. So kind of the consequence of this is that you're left choosing between consistency or availability as your other 2 options. In reality, that's not exactly what the theorem says. And as this quote gets at, the way that you usually work with the CAP theorem in practice is to find different combinations of availability and consistency that allow you to still meet the goals for your system. But what you get with the COM theorem here is a recognition of the properties that need to be upheld in order for you to achieve all three of these goals, essentially. And I guess I'll briefly describe what these 3 goals are. So consistency is basically saying that all of the replicas within the system are going to agree on the result under some consistency model. Availability says that you're always guaranteed to get a result if you make a query. So there's not going to be a situation where maybe like the node that you're accessing is down and you're just getting a timeout, for example. There's always a node that you can get a request or get a response back from. It's under the event of a network partition. You have some large cluster of nodes, and at some point in time, not all of them are going to be able to communicate with each other. And the system needs to continue working under that eventuality. With the COM theorem, though, you actually manage to achieve, when you have logical monotonicity, you actually manage to achieve all three of these goals, because you're dealing with these situations where the computations that you're doing are logically monotonic and can always operate under these subsets of data while progressing towards the like final calculation that you want. And so even when you have a network partition, you can just continue communicating with whatever nodes you have access to. And when that partition is eventually healed, if it is ever healed, they can just merge all of their results back together, essentially.
Yeah, so you don't get consistency at all times, as in not everyone has the same state, right? But you're consistent enough in that you can continue making progress. So there's two properties that they actually don't talk about in this paper at all, which are progress and liveness, I think. So we're not saying that all machines can actually talk to each other at all times and actually exchange information, but in aggregate, if you kind of zoom out, on the time level of the entire transaction, then or session, I guess, then you don't have to drop data and make things consistent again. You can always reheal the state. But I also found it interesting. So like we're talking about, you get all these things. This idea that, well, sometimes you need to drop out of eventually consistent mode and go into like a full consistency mode. And it gives you a way of thinking about both. So the shopping cart example, I thought was really illustrative. Where if you're adding things to a shopping cart across multiple devices, I guess you have a shared shopping cart with a bunch of people, for example, or many machines that are watching the shopping cart. Adding ththings in, that's fine. But when you want to go and actually check out, you either have to all agree these are the things, or after the fact, send us an apology email because you're actually out of inventory. And I mean, I personally don't really like that, the apologizing version, but it is, and in the case of, say, retail, that's probably not the greatest experience, but you can definitely see cases where it's like, you're typing into a shared collaborative document and you get into just a bad state where people are typing over each other or something. And that's possible, and then people are gonna have to go and clean it up. Philip.
I think I wanted to point out that example as well. There's something I don't quite understand. I think they're saying that nowadays you don't actually need coordination for the checkout. I don't understand what they did to avoid it though. They're saying something about, I think the checkout operation is enhanced with a manifest from the client of all its update message IDs that preceded the checkout message. Replicas can delay processing of the checkout message until they have processed all updates in the manifest. I don't quite understand what that means and how that like achieves the idea of like avoiding coordination. If someone has like some idea, that would be great.
Yeah, so it's basically the difference between telling the server, check out my shopping cart, and telling the server, check out my shopping cart with these items. In the first case, the checkout is going to result in a checkout with whatever items that replica has seen. In the second case, you are basically giving it a log of the requests that you have sent so that it is able to defer processing until it is in a state that is consistent with your local state.
Okay, yeah, that makes a lot of sense.
Mm-hmm.
Yeah, and so it might not just be like literally these items are in the cart, but even the last time that I saw state from everybody else, just like a vector clock, right? I saw these states and here's my items, right? And then when we merge that together, will that put me into an inconsistent state or not, right? And so we can kind of know when information came in. And sorry, I realized that was relatively dense. Do I need to unpack that? Does that make sense? Okay, great.
It's a little bit like the operation-based CRDTs from last time too, where in that case, we don't just have these purely commutative events. They may have dependencies on themselves that need to be processed before they can be processed. But by making those dependencies explicit, whether with like explicit causality checking or vector clocks and so on, you can make sure that you are deferring processing until you're ready to handle them.
It doesn't mean that you're possibly, sorry, does it mean that you're possibly likely to like bottleneck performance there as well?
In cases, in the cases where the information hasn't reached things in the first place, which should be hopefully rare. And in cases where, more important, the not delaying would cause an error. So you want to bottleneck in that case.
Yeah, I think it was, I think it's this paper. They mentioned that they got some huge speed up by not worrying about coordination on like the normal case. And we also see this in other, and anyone in Vision is going to laugh because I bring up software transactional memory like 40 times a week. Optimistic concurrency also gets this speed up of like, well, you might have to retry things, but because we're not in by default locking and doing coordination, you actually get a massive speed up in the normal case. But yeah, sometimes if you need consistency or you need to do replication for some reason, then you can, because of latency and partitions, you could in concept have unbounded delay, right? Like it could be literally infinite, at which point you may want to put things into, and they talk about this a little bit, right? Where you may want to put things into a synchronous system, something like Paxos or Raft, where it's like, well, whoever we didn't hear about at this time, we're going to pretend that they're down and keep moving forward. And so having that one theorem to talk about both cases is really interesting, because now it's not this or that. It's like, well, we can talk about this gradient of consistency and coordination freeness, and you can kind of move from one to the other. And this section here that I've pulled up, I guess I'll just, well, oh yeah, no, that's awful. Monotonic programs don't need to know all of their peers even. So it's not even, I was talking about the spectral clock, like maybe they have 1 million peers and they don't even know their membership, right? Like we can do that, but then you can't get consistency across them necessarily at any one given point in time, because you actually need to know the membership. So they're making this distinction there as well of some of the conditions you would need to know.
This reminds me, and I'm not sure it's related, but what we said about going faster, but theoretically it could go slower in rare cases, but still, I think on the average, you're moving faster. It reminds me very much of the throughput versus latency balance in a lot of very, high level data, big data systems, and where they sacrifice latency for throughput.
Mm-hmm. Yeah, so do you want to talk a little bit more about that in detail? I think that's a really interesting counterintuitive concept.
It's not something I know in depth, but basically a lot of big data operations, they gain performance by working on huge volume, but it does mean that they don't, how should I put it? It's in a way, it's the batch versus immediate, right? They're faster because they work in batch, but that means you don't have the immediacy of just-in-time processing. And when you apply it to big data, you don't know when your thing will be processed, but you know it will be processed fast when it is processed. And overall, on a big system, it's worth it. If you're waiting for an answer now, not so much.
Yeah, it's and like all of that, absolutely. And then the one extra bit is throughput optimized thing, you may get very, very fast results, but they're not consistently fast. So the system may wait for, you know, however many messages and then process and batch. And if you were the last one, maybe you're going to get that back immediately, right? So it's about consistency, I guess, of latency as well.
True. Thanks. So yeah, I'm not sure it's fully related, but there is something there that reminds me of the edge cases are similar in structure. One thing I must admit, reading the article a bit fast and a bit in diagonal, and I can see how monotonic gives you cap resistance. The converse is a bit less obvious to me, and I'd like us to go in a bit more in depth into that. That would.
So I think the idea with that is that they use a very specific meaning for coordination, because basically the way, at least in the sketch, they say that they prove the opposite direction, the only if direction of the thesis statement of COM by showing that monotonic programs don't necessarily require coordination, and they define coordination as like a coordination message is one that gets sent no matter what order all of the like internal messages get sent in. So even if everything is optimally ordered, there's still going to be a coordination message. Whereas in cases where like there isn't something that isn't a coordination message is one that you can avoid depending on, or could be avoided by depending on the order that all of the operations come in at, I think.
Yeah, it seems to me that, thank you, that's useful. It seems to me there's still a kind of, okay, so non-monotonic operations require this kind, okay, that's the missing piece, really. If you're non-monotonic, then you need coordination. That's the crux.
Yeah, so like I think one maybe good intuition on this, right, is like, let's say that you have a mutable register and it's not using a CRDT with tombstones underneath, let's say, right? You're just setting new values on it. Well, now we have to have some way of agreeing what the current value is, because it was 1 and now I set it to 10 and now I set it to 6. It's kind of all over the place. So we have to agree. If we have tombstones and tracking of the provenance of all the data and, you know, what the update knew about, then we can stitch that together and know and agree without coordination, without ahead of time coordination, without locking some period of time that this is where we would have gotten to with these updates. So you can have a non-monotonic implementation or a monotonic implementation of a mutable register, as an example.
I'll have to look into that. Sorry.
For a second, I thought that like these coordination messages are overspecified in a way. So I was thinking like there are some things that seem like, for example, in my head it was coordination messages are messages that you need to send everyone, but that's like overspecifying it. It's messages that you need to send everyone, even in those weird cases where all of the data is in one machine, right? I think that is really the insight. I think the paragraph there in the top left really captures it.
I'm not sure if I misunderstood you. It's possible you said this correctly, but I want to make a distinction between a message that needs to be sent to everybody and a message that always needs to be sent. It's possible that's what you said. But
yeah, that's the point. That's like the misunderstanding I did in the very first time I read it.
Okay.
I was thinking, oh well, but there's a lot of messages you need to send everyone because you need to send everyone, tell everyone about this thing. But sometimes like it makes a difference whether you need to send this message in all cases or in all partitions of your data. Because sometimes there's, like, for example, let's say in the log-free thing, right, in the deadlock detection algorithm, if all of your what is the reason there, logs or whatever are all on the same machine, then there is no need to communicate with anyone else to detect all the deadlocks. So in those cases, you don't need to send everyone the message, right? So it's not
also. Sorry, go ahead.
Yeah, so coordination messages aren't needed in that case to produce a valid output.
I do want to nitpick one tiny thing. You had mentioned that there's a lot of messages that need to be sent to everybody, but that is actually a stronger result than we're talking about with COM here, because COM is working with sets and subsets of data. It's not saying that all of the replicas are going to have the same result. It's saying that if you've seen a subset of the data, the result that you have is going to be a subset of the total result. So there can be some node on the network that undergoes a network partition with the others, and that partition never recovers, but that's okay. It won't end up in the same state as every other node, but the state that it's in is going to be a subset of their state.
Or that's okay for some use cases.
Yes.
Right. Or at least that's okay in that these properties still hold, and that if you were to, in the CRDT property, right, like if you see the same events, you get the same state kind of idea.
Yep.
But that would be terrible if you were, I don't know, doing bank transfers, for example.
Sorry, folks, I'm just trying to speed read the full proof. And absolutely fascinating corollaries. The equivalent of Q is monotone, can be distributed by a transducer that is oblivious, and expressible in data log is part of the equivalence class. There's explicit data log. Yeah, no, there's a lot of fascinating further results in the full paper.
By the way, about the monotonicity, is anyone else, like, I'm at least irritated a little bit by the fact that they model programs as essentially, if I understand that correctly, kind of like a function from a set to a set, and then define monotonicity on, like, set monotonicity. It seems weird because, like, how do you encode other programs, or is that like a sufficient kind of encoding, or would maybe a, I don't know, different version of program also work? And or like, can you turn any program that I want to write into this kind of function or something? I don't know. It seems weird.
I think they sort of intentionally didn't worry about that because that would require like a much, I don't know, bigger, serious, heavy duty proof. So they're not doing a constructive thing where they're like telling you how you can construct a program. They are instead just like drawing the circle around the programs that do and don't work with this. I think was the thing, and the fact that they don't care about what's happening in the middle, they only care about the beginning and the end. I think they sort of mentioned it a couple times, is kind of a big deal for the way that they did COM. And so you'd have to do something totally different if you wanted to be concerned about the like structure of the program or the order of operations in some way.
And importantly, you asked if you can take any program that you want to write and fit it into this model, and no, you can't. There are only small classes of programs that can be written monotonically like this. And that's where a lot of static analysis that they talk about with Plume comes in. I think it was possibly Brooklyn earlier who mentioned like the checkout example, where they might offer you a coupon to deal with the faulty checkout. And even though that might not be the right solution, I think it's a very powerful example of where this sort of result comes in handy, because it makes the parts of your program that cannot be represented monotonically explicit. so that you can see where the computational model that you're working under does not align with the real world and with your business needs. So that rather than ending up with emergent failure that you need to deal with as it comes, you can be very explicit about the failure cases that your application may undergo and how you want to address those.
Yeah, so there's like the COM theorem describes both cases, right? But of course we want the monotonic one whenever possible, but it might not be practical to do. And they have, I'm trying to find the quote, but they have something in
Bottom
here
right of
about,
your screen. Above
where it's like,
section 4.
bottom right
Possibly.
here. Yes, yeah, exactly. This provides a bright line, literally a bright line. Raises all the questions, et cetera, but like it might be too difficult to do. And so in the same way that, with implicit concurrency, so there's this idea where you can analyze a dependency graph and then automatically parallelize the parts that don't depend on each other. So like Facebook does this, for example, for their spam filtering stuff and queries on that data. And just, where the program will just write, yeah, here's a bunch of stuff, and it will figure out how to do the parallelism. It's the same sort of thing where it's like, well, these are the bits that are coordination free. And then these parts are going to get depend on some kind of a coordination. And so you could automate parts of that away for some classes, but not in general. And so if you can keep it in the same way that you want to have a pure core, like a functional core and an imperative shell, could you have a monotonic core and a coordination shell on your program?
I think what grinds my gears there so much is they say it's a bright line between like these programs, they don't require coordination, and then these ones do. But it's only a bright line if you understand exactly how you can map your problem, which could be of any form, into this weird kind of function that takes a set as input and a set as produces a set as an output, right?
Yes, but like maybe an extra bit of context is it's not that the, say, state of your program is a set. It's the messages that we've passed to each other to construct the state and to run a view over that is a set. So your database is set-like, but you might pull more structure out of that.
Okay, actually, I'm less unhappy about the input being a set, but more about the output being a set, right?
Well, it's saying that the transition function has to keep you in a set. And then on top of that, you can take that set and do whatever you want to it and read from it. Right?
Think of a graph, for example. A graph can be described as a set of nodes and edges, right?
Mm-hmm.
And a graph is a rich structure, but it's set of node and set of edges. So it's you can think of your output as a set, and it's still a graph.
I mean, yeah, you can encode a lot of things. Well, you can encode everything as a set, but the problem is sometimes you have invariants. For example, you'll have your graph and you'll have an edge between two nodes you don't even know about. Mm-hmm. So how do you do that then, right?
Yeah, and so sometimes if you get a incoherent update, your view function will have to ignore it.
Yeah, and especially when you have if you put causal dependencies, as we said last time, right? If you say this datum depends on that datum being there, you haven't received it, then you put it in the ignored bin until you receive what it depends on. And you have an incomplete picture. That's the whole point. You have an incomplete input, you have an incomplete output, which is fine.
Yeah, and I think the other reason that they're using sets in particular is that it's a very, very weak set of constraints. If they said you need this specific data structure, well, now you're really stuck in that one thing. But sets can be used to describe such a broad class that if you wanted to use a DAG, that's okay, because a DAG is a kind of set with more structure on it.
Yeah, I would avoid getting too hung up on the notation of subset here. This definition holds equally for like a semi-lattice using the like comparison operator, just saying that the two outputs the one output needs to be less than or equal than the other.
That's what I had in the back of my mind. But then I wasn't quite sure if that works, or my version was, and I don't know, because like I guess I don't know about semi-lattices enough, but my version was like, you need to have some partial order on your output. Yeah, and if so, why did they choose sets? Just because it was simpler and everyone else would like see, well, you can use a semi-lattice, no problem.
Yeah, maybe the other way of thinking about this for what they're trying to prove, right, is that a monotonic program is something that only accrues data and never removes it, because removal is not time symmetric, right? It's like we're not, we now have to coordinate on, well, what was removed. But if we have, say, a tombstone set as removal, but that's really just adding data into the set, right? So as long as we have a grow only set of some kind or sets, then it works, and you can impose whatever structure on top.
And if you want things to be added, then removed, then you had causal links.
Yeah. Or vector clocks or some kind of tracing. Yeah.
Yeah. But yeah, it would be interesting to see if we can rewrite that in the semi-lattice language and if it's equivalent in terms of proof. Very likely. I'm having a quick look at the Bloom language spec and trying to understand how it's related, but not doing that in real time is not working, sorry. But they're basically saying there's this base notion of unification of sets. And yeah, sure, that's the base construct. And you can express a lot with that, and which makes perfect sense to me.
Yeah, I love
Bloom
the Bloom.
is essentially, sorry, go ahead.
Oh, I was just gonna say, I love the Bloom tagline, which is something like disordered programming or something to that effect.
Yeah.
Yeah. Sorry.
It's too bad Bloom was not pursued.
Oh, yeah, they have an implementation.
No, but I mean, it stalled. It's didn't develop. No commit after 2013. I wonder if there's other implementations of these ideas in other systems, because it doesn't seem fundamentally hard. Like, it should be possible to write a library in most programming languages that has the base constructs of Bloom and expresses that as a module in pretty much anything. It doesn't look like
the most mature. Yeah, that's what I was going to say.
Please.
Oh, I was going to say the most mature continuation of these ideas is Christopher Meiklejohn's LASP, which, so my internet's cutting out, but it's basically a language for working with SRDTs that was integrated pretty tightly into an alternative distribution runtime for Erlang. Unfortunately, he started pursuing a PhD on something else, so that project has also kind of fallen by the wayside. But
so last language by whom?
LASP, LASP, by Christopher Meiklejohn.
I'll post a link.
Yeah, I got it. Okay. Thank you.
And he has some nice talks on this stuff as well.
I wondered if Pony had anything like this.
Sorry, go ahead.
No, go for it. You go.
I don't believe Pony did. What I was going to say about Bloom is, just to answer Mark's line of inquiry, Bloom is essentially data log under the hood. It's just working over like a monotonically growing set of facts, which it defines essentially semi-lattices over for things like sets and counters and so on. And then you are building like tabular views over that data to structure the state for your application. But then it does static analysis to detect all of the places where you have non-monotonicity through something like negation. so that it can recommend that you drop something like Raft in there.
Oh,
Actually,
it's a
would Datomic fold some of that in? Then I'd love to. Has anyone worked with Datomic at all? It's quite hard to get hold of, I guess.
Yeah, so Datomic is has strong consistency under the hood. So they have transactions like ACID transactions in their system. It's not a fully distributed data log. If you want a fully distributed data log, you should follow what Quinn and I are working on, but that doesn't actually exist yet. So
With bated breath.
hopefully something soon, next several months. But really pulling ideas from papers like this, which is probably why Quinn and I sound so familiar with this one. So.
There was I agree with Brooke that the user experience that they described with the shopping cart apology coupon is subpar, but the idea that they point out where there's like it's useful to pay attention to like you can have multiple acceptable endpoints in your for your program is kind of neat. I thought that was a useful nugget to keep in the back of my mind going forward.
Mm-hmm.
Yeah, absolutely. I think that's a lot of what you get from a lot of modeling languages like Alloy and TLA Plus, for example. People will sometimes get upset if someone brings like Alloy into a project and says, hey, your design is wrong because Alloy doesn't tell you how to fix the design, but it's still useful to know that there is something wrong that needs to be fixed, possibly through human means.
A heavy dose of like pragmatism sort of reminded me of the saga pattern a little bit as well, where there you're kind of saying like, oh, like, yeah, you might not actually be able to undo it, but you can sort of like semantically undo it. It felt kind of similar in a weird way. Like,
Awesome. So we're coming to the home stretch here. We have 8 minutes left in the time slot. So does anybody have any final burning questions or parting thoughts or things that they're excited about with COM?
Oh, there was a neat connection that I noticed to at the end of the paper. They're talking about languages, not just Bloom. I think they mentioned a bunch of other languages that are like doing similar things to Bloom. There were a bunch of something logs that sounded interesting that I'm probably going to look into. But the interesting connection though was that Quinn just gave a talk about how like domain-specific languages are useful and important and relevant, and it seemed like a handy connection.
Keep calm and carry on. Love it.
Yeah, thank you for pointing that out, NA. But that's actually connected to the quote I wanted to say, which is page 6, 3.3. When they introduce Bloom, they say, we felt that a good language for a domain is one that obscures irrelevant details and brings into sharp focus those that matter. And it probably doesn't need to be said that that's my philosophy about programming in general, but I think that anytime we have a problem in software that's extremely difficult to solve with the tools that we have, that probably points toward us needing to make better tools for solving that problem. And I think Bloom here and Daedalus, which Bloom is based on, are really powerful examples of that idea. And yeah, I just, even outside of distributed system stuff, I think that that point is something to really take away from this paper here.
Yeah, I think even for on a single machine, it's interesting, right? Because humans are terrible at concurrency. We think sequentially, like completely, and all of our concurrency, or not all of, a huge portion of the concurrency that we've done historically has been trying to reduce it into some kind of sequential thinking. And this gives us two advantages, right? Automating away concurrency and automating away huge chunks of having to think about distributed programming, which is even harder, right? When you have partial knowledge or failures on external systems. And when you can get into this monotonic subset and then having automated tools tell you, hey, this is going to be coordinated, that's going to be coordinated, is super interesting.
The thing I keep coming back to as well, we keep saying like single machine and stuff when we're talking about distributed systems, but if you think of like CPUs, you can have like multiple, right, like logical CPUs or whatever on one computer. So even that is like a distributed system in some weird way, right? And so there's a lot in here that I'm always like, oh, I wonder if that applies like on a really low level.
It absolutely does.
Yeah.
No, that's an awesome point to bring up. And a lot of the early work on a lot of these coordination protocols had to do with handling locking when dealing with multiprocessing and multi-threading and so on. And the way I always think of distributed systems is that a system becomes distributed when we need to care about the speed of light.
Yeah. Or there's the it's a Lamport quote. A distributed system is one in which a failure on another system causes your system to become unusable. And so that could be two processors. You have a multi-core system, and one of them, you do work sharing, and one of them gives you a false result, right? Or refuses or crashes and doesn't have a result, just goes totally offline, right? And now you're in a useless state.
Heck, even like your CPU and your RAM is like just a single core. Even like that's still there's two things that are talking to each other there.
Yeah.
I don't know how many of you are here for the first session of the reading group where we read Nancy Lynch's 100 possibility pools in there. It just had to do with sharing memory cells, entirely abstracted away from the notion of servers or nodes or clusters or anything like that. It's just if there are multiple things that you can read and write to the same blob of memory, then there's coordination issues that you need to work around somehow.
Thanks, Adam. Okay. So 2 minutes to go. Maybe I'll use that to wrap up then. So at least I personally really enjoyed the session. I think we had like a good discussion, and talking through stuff helped me think through a few things as well, which is always a nice end result. This is obviously a bit of like a lighter paper. It's not like heavy on math and proofs and stuff, right? And it's not 30 pages long. So I think this is kind of a nice sort of sweet spot for this group, where we can kind of digest something. You can read it in whatever, half an hour or an hour, and then have a good discussion with it. Next month is on, let me pull it up here. I actually don't remember, but we only have one more scheduled, pre-scheduled. Making CRDTs Byzantine fault tolerant, which is a very recent paper from a couple months ago. It's a Martin Kleppmann paper on both making following causal links and also structuring a CRDT in a way that is Byzantine fault tolerant. If you have other things that you'd like to read after that, please drop me a line. That's in Discord or via email or on Twitter, all of the above. If anybody wants to host one of these, also very allowed. And thank you everyone for coming, especially the people who showed up for the first time. And hopefully see you all next month. I'm going to stop the recording now.